So now we get to the data structures part and how we can represent our graphs. So again, so far we've really talked about all mathematical and a little bit of visual. Now we're getting into how do we store the damn thing into the computer. And the first way is using an adjacency matrix. And it's the same matrix that you and I love, a 2D array, that frankly we're also pretty familiar with using with as well. There's goods and bads. So in the matrix that you have here, here's the visual representation of it, and here's what we would store behind the scenes. Now in this example, it is an undirected graph, so you'll frankly see a mirror. What I mean by that is that we have a connection from 1 to 2. So notice, again, we have starting off at 2, are we connected to 1? And we have a 1 here. So the 1s and 0s in here just mean trues and falses. So instead of writing trues, I just did 1s and falses 0. Notice also is that we could do it the other way. Is 1 connected to 2? That is true. So notice right along the diagonal there is going to be a mirrored effect for all of them. So look at 5 and 4. You'll notice that 5 is connected to 4 is true, and then we go from 4 connected to 5 is true. So notice there's going to be a nice mirroring again when there's an undirected graph because it goes both ways. For a directed graph, it's completely different when it comes to the representation of it because it is directed. It's not reciprocal. So if you look at the 1 and 5 that I have highlighted from you, you'll notice this time I have a from side and a to side. So in the example we have a 5, 2, 1. So we start from 5 and go to 1, and we're going to say that that is a connection and set that to true. But notice it's not the other way around. From 1, is 1 connected to 5? No, it is not. And frankly, well, let's leave it at that. So this is very different. And again, for a directed graph, if I went down the diagonal here, notice it's not a mirror because I'm sure there's going to be some vertices that aren't connected, well, back and forth. Let's put it that way. But the overall set is still set up for exactly, well, here's a nice matrix, and it's nicely set up. But I want you to notice a bad thing. There's a hell of a lot of zeros and falses in there, isn't it? That's a lot of wasted space that's going to be taking up more and more space as we get more and more vectors because we have to do a 5 by 5 matrix for this one for the number of vertices. What if it's 8 by 8, 1,000 by 1,000? We're making a massive matrix that frankly might be mostly empty unless you have a lot of edges. And this goes back to our sparse and dense graph material that we talked about earlier, and that is that if we have a lot of wasted space in a matrix, we may just have another solution instead of using a matrix. So one last one I wanted to show you is an adjacency matrix for a weighted directed graph. So this time you're going to see all these numbers in here and go, wait a minute, well, follow the same thing. 5 to 1, and we have an 8 as our weight. Well, if we go to from 5 to 1, there's our 8. So think about it as in any positive number happens to mean that it's true in this application. I know some of you are going to be like, well, what if you do? I hear you. You would have to adjust for it if they're negative numbers, or, well, I'll just leave it at that. There's some adjustments we would have to make for other applications. But this one works out pretty good. But again, notice all of the zeros that are in there. Is there a better way to do this if there's not a lot of edges?